In this lecture, we will define the degree of a continuous map between compact-oriented manifolds without boundary of the same dimension, and we will see that it is a homotopic invariant. Moreover, we will provide two applications of the degree, namely the fundamental theorem of algebra and the Hairy-Ball theorem. This is the last result that we saw in the previous lecture. And we are going to repeat here the statement of this theorem because it's going to be crucial to show that the degree is a homotopy invariant. So let W be a compact-oriented manifold of dimension n plus 1. W is a manifold with boundary. And let M be a connected compact-oriented manifold without boundary of dimension n. Now consider a C-infinity map defined in the boundary of W and whose target space is n. Okay, and let Y be a regular value of such a map. If we can extend this map to the whole W as a C-infinity map, and moreover, Y is also a regular value for the extension, then the degree of the initial map at its regular value Y is going to be equal to 0. As a consequence of the previous result, we have the following corollary. Let F and G be C-infinity maps from M to N, homotopic C-infinity maps, where M and N are compact-oriented n-manifolds without boundary, and N is connected. Now consider a regular value Y for both F and G. Then the degrees of F and G for the regular value Y are the same. So what we can consider is H being a homotopy, okay, between F and G. A priori, a homotopy is just continuous. But we can suppose, since F and G are C-infinity, we can suppose that H is C-infinity in the neighborhood of the union, too many O's, in the neighborhood of the union of M times 0 and M times 1. This can be done, for instance, by replacing our homotopy by another one that is constant in the neighborhood of 0 and 1, so that the map HD in the neighborhood of 0 is equal to F, and the map HD in the neighborhood of 1 is equal to G. That's very simple. Okay. In particular, H is going to be transversal to the point Y in the neighborhood of that set, okay? M times 0, 1. And by using our results that say that transversality is an open and dense property, we can actually suppose that H is C-infinity. It's a C-infinity homotopy that is still transversal to the set consisting just of Y. So indeed, what we can suppose is that we have this condition everywhere, right? So we have that capital H is transversal to Y, and it's also true that the restriction of H to the boundary of our manifold is transversal to Y, because that's a hypothesis. It's because Y is a regular value of both F and G. So we can apply the theorem, and that implies that the degree of H for the regular value Y, and now we need to give orientations to M and N. So the orientation of M is going to be omega, and the orientation on N is going to be theta. So, and of course here is not H, but the restriction to the boundary, okay? And now we have to consider the orientation induced by the orientation omega times omega 1 in the boundary. Okay, so this is, and finally, the orientation theta, and that's equal to 0. So let's unpack this formula over here. First of all, the restriction of H to M times 0, which is one of the components of the boundary, is just F. So we have the degree of F for the regular value Y, and now the partial of the orientation omega times omega 1. But we already saw that that's going to be indeed omega. So we have here omega and theta, sorry. And now we consider the restriction of H to M times 1, which is G. And that's the degree of G for the regular value Y. And we have to consider partial of omega times omega 1 for M times 1. And we already know that that's going to be minus omega. So minus omega theta, and that's going to be equal to 0. But obviously, this implies that the degree of Fy with the orientations omega and theta, the orientations of M and N, minus the degree of Gy with the orientations omega and theta is equal to 0. Because if we replace here minus omega with omega, what happens is that the degree is multiplied by minus 1, sorry. So as a consequence, the degree of F and G at the regular value Y and its common regular value, it's equal, the degree of the difference is equal to 0, and so these degrees are equal as we want to prove. Now let us see how the degree varies when we vary the regular value. Okay, so we are interested in considering a C-infinity map between M and N, where M and N are compact oriented manifolds without boundary of the same dimension N, and the target manifold is connected. Now consider Y and C two regular values. What happens is that the degree of F at both regular values is the same. So we are going to use first that N is connected. We are going to give an idea of the proof. Since N is connected, what happens, what we can prove is that given Y and C 2 points, any 2 points of N, there exists diffeomorphism, a C-infinity diffeomorphism from M to N, such that this diffeomorphism phi is homotopic to the identity map, and moreover, the image of Y is equal to C. That can be proved. It's not very difficult. Indeed, we can actually define an equivalence relation between points of N of the following kind. 2 points are related if there exists a diffeomorphism satisfying these conditions, and we can prove that the equivalence relation has classes that are open sets, and as a consequence there is just one class because N is connected. Okay. What we can do now is calculating the degree of phi of f composed with phi at the point C in two different ways. Okay? C is a regular value for the composition because y is a regular value for f. And indeed, this is going to be the product of the degree of phi for the regular value c times the degree of fy. But what happens now is that phi is a diffeomorphism, so this is 1 and minus 1, 1 or minus 1, sorry. And since phi is homotopic to the identity, and c is a regular value for both phi, because phi is a diffeomorphism, and for the identity, then, and both of them are homotopic, this is the degree of the identity at C, which is equal to 1. So we can just forget about it. Moreover, we know that phi is homotopic to the identity, which implies that the composition of f and phi is homotopic to f. And C is a regular value for both these maps. So as a consequence of the previous theorem, this implies that this degree is the degree of f at C. And we just proved the result. The degree of f for the regular value y is equal to the degree of f for the regular value c. We want to define the degree of a continuous map. And so it is natural, since the degree is an invariant of homotopy for C-infinity maps, to see that every continuous map is homotopic to a C-infinity map. More precisely, let F be a continuous map between M and N, where M and N are compact, oriented, N manifolds without boundary, and N is connected. Then F can be approximated in the space of continuous maps. For the weak or strong topology, it doesn't matter because they are the same, with C-infinity maps homotopic to F. Okay, let's see that. We can suppose that the target space is contained in Rp because of the Whitney embedding theorem. And now we can consider a retraction from some open subset W of N in Rp to N. This is a retraction, is the retraction given by the tubular neighborhood theorem. W is an open neighborhood of N in Rp. Okay, now fixed a map F0, a continuous map from M to N, okay? And we want to approximate it with a map that is infinity, very close to F0 and homotopic to it. So in any neighborhood of F0 for the weak or strong topology, as I said, they are the same, there exists a map F1, which is C infinity, that approximates F0. This is just one way of saying that if we fix a neighborhood of F0 for the strong topology in the space of continuous map, there exists a C-infinity map F1 contained in that neighborhood. Okay, and now we can consider the natural homotopy because we are in Rp. The target space is in Rp. So we define Ft as the convex combination of F0 and F1. The issue here is that if this is N, and now we consider our tubular neighborhood, what we are doing when we fix X is a convex combination of points in N. But what happens is that this convex combination it's in general not in N. So in order to somehow have something defined in N, we have to consider the retraction. Okay? So consider the composition with the retraction. Now this is a map defined from M to N, and it is obviously a homotopy. The problem is that if F1 is not very close to F0, this could be not well defined. Because if, for instance, we have a point x such that the image of x by f0 is this one, and the image of x by f1 is this one, the segment is not contained in the domain of the retraction, so this is not well defined. But this never happens if the points are very close. In this case, the segment joining the two of them is contained in the domain of the retraction. And so, if f1 approximates f0 well enough, this is well defined, and indeed, it is a homotopy between f0 and f1. And what we proved is that any C-infinity map, or any C0 map indeed, that is sufficiently close to f0 for the weak or strong topology is indeed homotopic to f0. Now we can just define the degree of a continuous map between manifolds M and N that are compact, oriented, and manifolds without boundary, and moreover, N is connected. Indeed, what we do is, given F, we consider a map F hat that is infinity from M to N and homotopic to F, and Y a regular value of F hat. And this definition does not depend on the choice of F hat or Y. Okay, we have that Y is a regular value of F hat, and F hat is homotopic to F. But if we consider another map and another regular value, for instance C, that is a regular value of another map F tilde, such that F tilde is homotopic to F, what we have is that, first of all, there exists a common regular value for these two maps. Okay, common regular value for the map F hat and the map F tilde. And now what we have is that the degree of F tilde for the regular value C is going to be to the degree of F tilde for W, because the degree does not depend on the regular value. Now, since F hat and F tilde are homotopic to F, they are homotopic. F tilde is homotopic to F hat. And so we know that this is going to be the degree of F hat for the regular value W. And now, since this degree does not depend on the regular value, is going to be the degree of F hat for Y. So the degree, this definition, does not depend on the choice of a C-infinity map, homotopic to F, or regular value. And so the degree is well defined even for continuous maps. In our definition of the degree, it is important that the manifolds are oriented. But we can give a definition of degree even in the non-orientable case. For manifolds that are compact, of the same dimension and without boundary. And obviously, the target manifold is connected. And this degree is not an integer number anymore, it's an integer modulo 2, okay? What happens here? The main result that we are using is that when we have a map H, okay, that is defined from W to N, okay, and we have a regular value for this is of dimension n plus 1, this is of dimension n, and we have a regular value y for both h and the restriction to the boundary, then what happens is that the degree of the restriction to the boundary is going to be equal to 0, okay? And the proof was actually considering this common regular value for h and its restriction to the boundary of w. And we had here in red the components of this set. Some of them are interior, some of them are actually arcs that intersect the boundary of w twice. And what we proved is that if the degree in one of these points is 1, in the other one is -1, okay? So the sum of the degrees in these 2 points that are at the ends of an arc in this set is always 0. If we are not in the orientable case, we cannot make that argument, okay? But what happens is that if we work in a field, let's say, in which 1 is equal to -1, it doesn't matter. It doesn't matter whether, it doesn't matter. We can make the definition of the degree, since that lemma is going to work, it's going to be true, even if we are not in the oriented case, that the degree of h, the restriction of h to the boundary of w is 0 modulo 2, that result is going to propagate along all the proofs that come afterwards, and in that way we are going to be able not just of defining this degree, but also proving that it is a homotopy invariant, okay? So what we saw in the last 2 lectures is that if we consider M and N compact N manifolds without boundary, where N is connected, we have that homotopic maps from M to N have the same degree if M and N are oriented. There, the degree is an integer number. And when they're not oriented, they have the same degree modulo 2. Moreover, if M is the boundary of W, and W is a compact oriented n plus 1 manifold, okay, and we have a map from M to N that extends to W, then we have that the degree of F is 0 when W and N are orientable, and the degree modulo 2 is 0 in any case, even if W and N are not orientable, okay? Now let us see a couple of applications. The first one is that a non-constant rational function of the Riemann sphere is surjective. Okay. Something that is interesting is that if we have a map between compact oriented and manifolds without boundary of the same dimension where n is connected, and this map is not surjective, then the degree of our map F is equal to 0. Indeed, the image of M is going to be compact. If it's not surjective, the set of points that do not belong to the image is open. But, and so what happens is that if we deform F a little bit, if we deform it very little, the maps are not, the close maps, the nearby maps to F are not surjective either. So we can suppose in this way that F is C infinity, and obviously the degree, this is because the degree of Fy is equal 0 if Y does not belong to the image of F. Okay? So a map that is not surjective always has degree 0. Now let's apply this result to the case of rational maps. A rational map is just a quotient of 2 complex polynomials in one variable, where the denominator obviously is not the zero polynomial, right? And what happens is that by the open mapping theorem, if f is not constant, then the image of f is an open subset of the Riemann sphere. Okay? So we can consider now a regular value in the image. This is possible because of Sar's theorem. Okay? And now what we are going to do is calculating the degree of f for the regular value w, right? And it's going to be the sum for c in the preimage of w of the degree of f at the point c. Okay, since w is in the image, this sum over here is not empty. There is at least one point in the preimage of w. And moreover, what we have for holomorphic maps is that they always preserve orientation. So these degrees are always equal to 1. So in particular, this is just the cardinal of the preimage of w, which is greater or equal than 1. In particular, since the degree is not 0, the map has to be surjective. Okay, since the degree of f is different than 0, then f is surjective. In particular, this implies the fundamental theorem of algebra, because a polynomial that is non-constant is an unconstant rational function. And we're saying, that the image of the polynomial as a map is the whole Riemann sphere. In particular, 0 is an element of that image, and so there is a root for any non-constant polynomial, complex polynomial in one variable. Okay? The second application that we are going to see is the Hairy-Ball theorem, that every vector field in a sphere of even dimension has a singular point. Indeed, what we are going to show is that if there exists a vector field in such a sphere with no singular points, with no zeros, okay, then as a consequence, we'll see that the identity map is indeed homotopic to the antipodal map. In particular, that implies that the degrees of these two maps are the same. Okay, but the degree of the identity map is obviously equal to 1. And the degree of the antipodal map is going to be, we already calculated this, -1 to the dimension plus 1. So this is -1, and we get a contradiction. What remains to be proved is this implication over here, that the existence of a vector field without singularities implies that the identity is indeed homotopic to the antipodal map, right? So let's see that. We are going to consider here in the sphere the point x and the point -x, and between these 2 points we have plenty of geodesic paths. The problem is choosing one of them. So we are going to consider a metric in the sphere such that the distance between antipodal maps is going to be equal to 1, okay? And what we want is choosing one of these geodesic paths. And we can do that by considering the vector field. The vector field is going to point in some direction, and then we can choose the geodesic path that has the same tangent vector. So we can actually, okay, consider gamma x the geodesic path from x to minus x determined by the value of the vector field at the point x. Now we can just define the homotopy. Ft of x is going to be gamma x of t, where we are assuming that gamma x is parameterized by arc length. Okay, this is for x in the sphere and t in the closed interval 0, 1. Since our vector field in particular is continuous, then Ft is going to be a homotopy, and F0 is the identity map, whereas F1 is going to be the antipodal map. And so these two maps are indeed homotopic. In this lecture, we defined the degree and we proved that it is a homotopy invariant. An interesting question is whether this is a complete homotopy invariant. And we will see in next lecture that when the target space is the sphere, then this is true. So that if we have two maps from a compact, oriented, and manifold without boundary to the n-dimensional sphere, and these maps have the same degree, then they are necessarily homotopic. This is Hoppe's theorem, and it's going to be the subject of our next lecture. Thank you for your attention.